Hello there, my name is Sonia Descartes, and today I'll be talking about my project benchmarking Taboo Search with IOH Profiler. So everyone can agree that the use of algorithms to solve problems is a fundamental part of computer science. While regular computational problems have definitive answers, such as red plus blue giving us green, other questions such as figuring out the best positional configuration for a set of surveillance cameras can have valid solutions that fit in within the constraints, but may not necessarily be the optimal solution. This is where we use algorithms to try and continually solve the problem until it reaches a stopping condition or finds a solution we deem good enough. However, some algorithms are better for problems than others. If there is a problem that you have that can only be solved algorithmically, then how would you pick between a local search algorithm or a genetic-based algorithm? Which would be the best for the job? This then raises the question, is there a way for us to determine which algorithms are better for the task and benchmark their performance for future reference? Well, this is where IOH Profiler comes in. IOH Profiler is an algorithm benchmarking platform. Put simply, it allows us to test out algorithms across a variety of platforms, then outputs a data set of performance ready for analysis. Before it, other algorithm benchmarking platforms were too specific in the algorithms they were observing and or the problems they were tested against. While designed with iterative optimization heuristics in mind, IOH Profiler still serves for general purpose and can be applied to algorithms across the board. The platform itself is made up of multiple modules. However, for this project, only the three most important will be covered. The first module we have is the IOH Experimenter. Experimenter, as the name implies, is the experimentation module of IOH Profiler and is responsible for the testing algorithms against the problems that we provide, or that we determine. In our case, we will use it to implement our own algorithm to then generate benchmark data. Next, we have IOH Algorithm. IOH Algorithm works like Experimenter with testing algorithms to then present us with some benchmark data. The key difference is that IOH Algorithm has algorithms built into the code and input variables such as budget and dimension that we can determine. And for this project, we will use it to benchmark established algorithms, which will then be used as a frame of reference against our own implemented algorithm. And finally, we have IOH Analyzer, the visual aspect of the Profiler platform and the key provider of analysis with two perspectives of performance. The first perspective we have is the fixed target runtime, which focuses on the distribution of the running times or the number of evaluations at different target values. Target values being the value of the solution found. This in turn answers the question of how many evaluations must the algorithm perform till a solution of specific quality is reached. We then go on to the fixed budget value perspective, which goes in the reverse direction, looking at the distribution of the best function values at various given budget values and answer what is the quality of the solution identified in a given set of evaluation. The way you can think of it is that one obviously looks at the runtime and the other one looks at the number of evaluations and the quality of those evaluations. In some respects, you can think of it as like the space complexity or memory. Now, the problems that the algorithm will be tested against are the max cut problem, where given a graph of nodes, we have to find the cut that splits the nodes into two different subsets that also goes with the cut also going through the most amount of edges in the original graph. This is an example of an NP-complete problem that can be a part of the IOH Profiler platform. Then we have the max coverage problem, where given a set of subsets that share some elements, we must find a k number of subsets, which is determined by the actual problem instance, a k number of subsets which will cover the most / have the most diverse set of elements. This is an example of an NP-hard problem that can be used in IOH Profiler. Now onto the actual algorithms. The first algorithm that we have is the Taboo Search, which is arguably the most important, as it's the algorithm of our own implementation used in IOH Experimenter. The way it works is, given a starting solution, it generates a neighborhood of solutions around it, and then searches through the neighborhood and keeps track of the best performing solution and places the previously selected solutions in a taboo list as to not retest them. And then the process is repeated for the current best solution until the stopping condition is met. Then we go on to the Greedy Hill Climber, which essentially looks at a solution and then picks the next variant of the solution with the best performance and ignores those that are less performing or go down in performance. This, however, means that the algorithm usually gets stuck in local optima and can completely ignore the global optima. And then finally, we have the randomized local search algorithm, which essentially randomly looks at a local area of a given solution by slightly deviating from the solution and tests the fitness of the new solution found. Now, by looking at all these algorithms, we can develop a hypothesis, which is that the Taboo Search will perform similarly to the randomized localized search and the Greedy Hill Climber. The reasoning being is that all of these algorithms, for the most part, have the same key principle of searching locally to find the next solution. Now here is the result of the algorithms on in the fixed target perspective for the max cut problem. As we can see, the taboo search has a high amount of evaluations at lower budget values compared to the RLS and the greedy hill climber algorithm. So lower budget value here, but a high amount of evaluations. Then for the fixed budget value, we can see that the taboo only has to have lower quality solutions for low amount of evaluations, but rises proportionally until it plateaus to be comparable to the others, albeit still being somewhat lower. So as we can see here, at high number of evaluations, it does reach a higher level of solution, yet at the start it's lower. So it goes proportional and then plateaus. Now here is the results for the fixed target for the max coverage problem. In the max coverage problem, it changes with the taboo list needing a lower number of evaluations to reach the same solutions as the randomized local search and the greedy hill climber. Now, there's an issue with like the actual iWedge profile platform in this instance, where it only generated one data set for the actual evaluations. So this is what we have to work with. In the fixed budget, however, what we can see is that the taboo list now has reaches higher budget values at lower level evaluations. So as we can see here, that the hypothesis has been completely blown out in that the taboo list and the greedy, compared to the other two algorithms, seems to just work completely differently. But the question is, why? Well, there are two possible explanations. The first explanation is that everything worked perfectly. While having the same principle, these algorithms are still fundamentally different and will have fundamental difference in performance. I mean, that's why they're even separated in the first place. If they weren't performing differently, there's no real need for the distinction between them. And in this instance then, if it works perfectly, the iWedge profiler succeeds in showing us the performance of taboo search in the max cut and the max coverage problem compared to the greedy hill climber and the randomized localized search algorithms. The second explanation is that everything went wrong and I completely fucked up. The actual possible cause is the actual implementation of the taboo search in the iWedge experimenter had issues utilizing the code infrastructure and actually performing effectively. Basically, the code that we wrote for iWedge, the taboo search was just not good. Which is a possibility and may not work effectively. Another thing is that within iWedge algorithm and experimenter, both had different constraints with regard to the inputting of the algorithms. For experimenter, we were allowed to input the algorithms, whereas iWedge algorithm, we had to input the actual dimensions and the evaluation numbers. And it needs to be investigated if these constraints were actually different, like between the two, and if there is a way to change them so that they can be the same. With the conclusion, then, there's essentially two. If we go by the first explanation that everything went completely fine and nothing went wrong, then the taboo search has a higher runtime and a lower budget value efficiency than greedy hill climber and the randomized localized search in max cut, and had a lower runtime and a higher budget value efficiency in the max coverage, meaning that whether in terms of performance, it determines on the problem. If the explanation 2 is correct, however, then the results and the conclusions drawn from them are incomplete or incorrect, meaning that more investigation into how the platform works needs to be done, and then the algorithm is then retested.